Good morning, welcome back to the class. In today's class we are going to discuss about the concept of 1.2 multi-computers and multi-processors. Multi-computers and processors. So this is 1.2 from your reference textbook 1, right? Now before I get into the concepts, I think somewhere in my introduction class we have came across the word multi-computer and multiprocessor. If I ask you what is meant by a multiprocessor or multi-computer, I believe that most of you could answer this question, right? But let me present you in a simple format of what this multi-computer and multiprocessor are meant to be. Basically both are meant to do the job. Somewhere they want to enhance the performance of the job that has been submitted. So for a layman, for a user, he is not concerned whether it is a multi-computer or a multiprocessor, but when you look into the system as a designer, there is a lot of difference between a multi-computer and a multiprocessor. Now that difference boils down to the way a memory is being used for accessing, because when you say a computer processing, always the memory comes into picture. The way the memory is being shared defines what type of approach is going to be used, whether it is a multi-computer or a multiprocessor. Basically the parameter that is used is a memory, right? Now let me draw a small figure. Using that figure you can make out what is a multi-computer and a multiprocessor, right? I am going to draw two figures. This is figure A and then this is figure B. In figure A, I am going to have one computer and then it has got CPU 1, CPU 2, CPU 3, CPU 4, right? In one more block I am drawing right. Now if you look into the block A, it is a single computer, but you have got multiple processors. In this scenario you have got processor 1, 2, 3 and 4, but in this second block you have got a multiple computers, computer 1, 2, 3, 4. Now if all computers wants to, when you use the word multi-computer, somewhere all this computer needs to talk to each other. So that is where you need to define some interconnection mechanism, right? Now this is how you can make out a difference between a multiprocessor and a multi-computer. In case of a processor, you have got n processors all sitting in one single computer, but here you have got n computers communicating or coordinating among themselves to accomplish a task, right? Now when I say both are meant only to enhance the performance of a system, or enhance the performance of a system is nothing but reduce the total time needed for executing a given job. Either it could be through multiprocessors or multi-computers working together for accomplishing a same task. So these are the two approaches that we are going to look into. Remember, both are meant for parallel programming only. When I say the word parallel programming, again it is to make sure that enhance the performance. So your parallel programming concept could be based on multi-computers or it could be on multi-processor models. For a multi-processor model, n processors are working, more than one working together. But remember, for all these n processors, you have got one common memory. You have got one common memory. But in case of multi-computers, each computer has got its own processor as well as memory. So each processor has got its each computer has got its own processor as well as memory. Here processor and memory, processor and memory. Right? Now I said no, memory is a one parameter that defines between this and this. Now in this case the memory is common among all processors. Simply I am going to call it as a shared memory concept. shared memory concept, but here, but is the memory shared here? No, the memory is not shared here, but each computing device, each computer has got its own local memory, clear? And one more thing is, each processor always communicates with the memory, but here every processor communicates with its own memory, local memory, and nowhere a processor 2 can access the local memory of another processor, right? No, direct access of the memory is not allowed in case of a multi-computer, but whereas in case of a multiprocessor, all processors are sharing the common memory. So, that is where the concept of multi-processor comes into picture. Now, if I ask you to list out the difference between a multi-processor and a multi-computer, what could be the difference, right? Is there any difference in the outcome of the function, outcome of either a multi-computer or a multiprocessor? No, both outcome is going to be same. They are meant to enhance the performance, perform parallel computing. But what is the difference that you see? The way the computing is done, the way the system internals are arranged makes it a difference between a parallel and a multi-computer model, between a multiprocessor and a multi-computer model, right. Now, I want you to list out the differences. So, once when you are able to make out the differences, then obviously you can better understand when we go into the various models of this and this, right. Now, I am going to give you 1 minute time. Now, list out the differences that you can make out between these two, the differences on the chat box. Right. Let me look into the responses and then come back to you, right. Now, the first one, what could be the first parameter that I can use for differentiating between a multi-processor and a multi-computer? The first one I am going to say is a memory. Now, this one is multi-processor, this is multi-computer, right. The first parameter that I am going to use to differentiate between multi-computers and multiprocessor is memory, right. Now, what is the, when I use the word memory as a parameter, now what will be the scenario in case of a multiprocessor? It is going to be shared one, right. But whereas in case of a multi-computer, is it a shared one? No, it is not a shared one. Each individual machine has got their own local memory. I won't say that different local memories are available. So, memory is going to be the first parameter, right. Now, let me look into the second parameter when it comes to the design, which is easy to design, right. Now, I think I am asking a hypothetical question. Design, probably if you look into some parameter, this is going to be easy, but if you look into some other parameters, this is going to be easy, right. Now, when I use the word design, if you have a very good interconnection mechanism, then probably designing this is a very simple one. But if you have a very good intercommunication among the processors, your bus structure etc. is so well designed that it can handle n number of address lines and control units, then this is going to be a easy one, right. Now, when it comes to the design, you cannot say which is the best one, because both has got their own advantages as well as limitations. Now, this design I am going to keep it as a pending till we look into the other models. Other models matlab when you look into the detailed architecture, then we will come back to this word design, which is the easiest one. But I would prefer to say that it is not that you could say this is better than this or this is better than this. So, that segregation cannot be made out here, because so many parameters are needed to be considered here, clear, right. Now, for example, when I say for example, if I look into the concept of say a scalability expansion, then I would say this is very easy for expansion. but this is very difficult for expansion, because if I want to increase the computing power, now this is very easy for me to expand the computing power, because simply I need to add four more terminals into it. But here if I want to add more processors into it, it becomes very difficult, because communication among the processors with the memory etc., is a very difficult choice, because as the number of processors increases, the communication becomes very difficult. So, somewhere scalability is a consideration. This is easy, but this may not be the one. But when I look into the other parameters, say fabrication, this is going to be very easy, but this may not be that one, right. So, likewise the design aspects we are going to put it as a question mark, and we will discuss in detail when we move across multiple architectures at an detailed level, and then we will come back to the word design, right. Now, the next parameter is, right, we as a Indians are very much worried about cost, the cost paisa, which one is cheap comparatively for fabrication, either this multi processor or multi computer, right. I believe that this is going to be considerably cheap, less cost than this, more cost, but this is going to be less cost when compared with this one, because here you need to, already the system is existing, you do not need to interface everything, you need to only provide a communication path, but here it is not the case. Comparatively the cost for fabricating this is less when compared with this, and I believe that this may not be a parameter, but we as Indians are very much concerned about the paisa cost. So, I am going to say that comparatively multi computers are far more cheaper for fabrication than multi processors. Clear? Right. The way they are joined together, I call the parameters coupling. The way they are made to work together, which is made to work very close together, either this or this. Now, I would say this is made to work very closely together when compared with this, because your computing power is very tightly coupled here, but whereas your computing power is loosely coupled here, right. Now, there is a concept called as tightly coupled architectures and loosely coupled architecture. The way your processors is made to work defines whether it is a tightly coupled or a loosely coupled. In that scenario, your multi processor is a tightly coupled architecture, but whereas your multi computer is a loosely coupled architecture. The way your processor is made to work together defines whether it is a tightly coupled or a loosely coupled architecture. Clear? This grouping, coupling or grouping, right. Now, grouping is a grouping of what? The computing power, the CPU. Here it is very closely grouped, tightly grouped, but here it is not so. Each computer has got its own processor. Again, the communication in a processor cannot communicate directly with the other processor. It can communicate only with its local memory, and if it wants to communicate, it has to through a interconnection network. So, that is why they call it as a loosely coupled one, but whereas this is a tightly coupled architecture. Clear with this? So, these are some of the differences that you can make out. And one more thing with respect to, one more difference that you can make out is, say, because if it is asked for 5 marks, you need 5 points, right. Let me add the 5th point, dynamic nature, communication of PEs, processing elements, right, which has got a easy communication among processing elements, whether this or this. Now, this has got a easy communication. So, I would say whenever a communication needs to be made from processor 1 to processor 2, it is possible, because all the processors shares the same memory and every processor can access the memory. So, automatically the communication among the processing elements is going to be dynamic in nature. Dynamic in nature, right, a very important observation. communication among processing elements, it is dynamic in nature. Because why we call it as dynamic in nature? Because every processor is connected to the memory, and communication is through the memory. So any processor, if wanted, can communicate directly, dynamically at any instant. Right. Now the same question I am going to put it in a multi-computer. Is it possible for multi-computers to communicate? The answer is no, because there you cannot communicate directly, it is going to be a static approach. So I use the word static approach. Why did I use the word static approach? In what sense I said it is a static approach? Because when you look into the way the computers are connected, now if you look into this, what is the scenario of these computers connected together? Now it is a ring topology, right? It is a ring topology. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 1, a ring topology, right? Or else even I can use this also. So what is this topology? This is basically a bus topology, right? Or else I can use even a star. This is a bus topology. Then I can use a star topology, right? Now the way you want your computers to be connected is going to be either a bus, a star, or one mechanism, right? One topology you are going to find, you are going to define, and that topology cannot be changed, right? Now for example, if I say I am using a star, now in case of a star, one-to-one connection is possible, but in the earlier one, when I said it is using a ring topology, now if P1 wants to communicate with P3, if your computer 1 wants to communicate with computer 3, is it possible? No, it is not possible. It has to be through computer 2 only. Somewhere there is a fixed nature in the way a communication is defined among the computers. With that sense, I am saying that it is a static approach, because the way your computer can communicate is static in nature. That static defines upon the way the interconnection is defined among the computing nodes. But whereas here the processors, since every processor is connected directly to the memory, each can communicate at its instance in a way it wants. That is why I call it as a dynamic approach, right? Now so communication among processing elements is going to be dynamic in nature, but whereas it is a static in approach. So these are the 5 differences that you can make out between a multi-processor and a multi-computer model. Clear with this? Right. Now if this is the scenario, you have listed out the advantages, you have listed out the differences. At the end, if somebody asks you what is the drawback of this method, limitation of this method, no, I would simply say, as I said earlier, no, the only limitation that is offered is going to be scalability, because your requirements of computing may not be same. Tomorrow if you want to enhance your computing mechanism, then probably this does not support scalability easily, but whereas this supports scalability easily, right? Now that is why this tightly coupled or loosely coupled, or sometimes it is called as shared memory, and sometimes it is called as distributed memory. So I am introducing a concept called as distributed memory, right? Now you do not see much application of a shared memory, but you see a lots of applications derived because of the concept of distributed computing mechanism, right? Distributed computing mechanism, because it allows scalability. The ease with which you can enhance is possible here. So that is why, because it supports scalability to a larger extent when compared with this is very widely used one. So most of the applications that you see are all derived from this, right? Because why most of the applications are derived from this distributed approach is because you are using the existing system, but you are defining a interconnection mechanism, and above that you are defining one layer. So that layer is going to define how you are going to share your resources, right? The way your resources are going to be shared is defined by the upper layer. one additional layer. So, a small modification to the existing one makes it possible for different applications domains to make it possible. That is why you see a lots of applications being derived from a distributed computing model rather than a shared computing model. Clear? Now, with this I am going to end my discussion on multi-computers and multiprocessors. So, then we will go into the various multiprocessor models. Your textbook has defined basically it has defined 3 multiprocessor models. Along with this, it has just made a mention of the 4th model. So, we will be discussing in detail those 4 model and then a 1 model for multi-computer. No remote connection model is been defined for multi-computer. So, this 3 plus 1 4 models we will discuss now. Right. So, parallel computers, right. Now, as I said, now it is basically into 2, whatever we have discussed earlier, it is multi-processor and then it is multi-computer, right, multiprocessor and multi-computer. Now, under multiprocessors again it is going to be 1, 2, 3 and then made a mention of the 4th one. The first one is UMA, NUMA, OMA, CCNUMA, CCNUMA. These are the 4 models: UMA, NUMA, COMA and CCNUMA. Your book has just made a mention of this CCNUMA, but a detailed discussion is made about UMA, NUMA, COMA. UMA stands for Uniform Memory Access, Uniform Memory Access, again non-uniform memory access, cache coherence, memory access, this, and then the last one, cache coherence, non-uniform memory access, right. This said no multiprocessor communication with the memory, because the memory is shared, the way you are accessing the memory is going to be UMA, NUMA, COMA or CCNUMA, right. The way you are accessing the memory, if every processor is given a equal access, then, or I would say a uniform access to the memory, then equal access is nothing but a uniform memory access. Say if there are 5 processors and all 5 processors are given a equal access to the memory, then it becomes a uniform memory access, right. Again it has got its own advantages and limitations. The limitations of this somewhere have made them to come out with another model called as non-uniform memory access. For example, if you are performing a computing operation, then you need a lots of data to be moved in and out of a memory, but you are performing a IO operation. When you are performing IO operation, either you are moving a data into the memory or moving a data out of the memory, right. Now, at that instance, if you allocate a processor, then the computing power needed for moving a data in and out may not be same as the computing power needed for processing a instruction or a equation, right. Now, at that time somewhere not every processor needs a uniform access to the memory. Now, that is where this concept of non-uniform memory access came into picture. Your processor is going to be divided into 2 and then based on the need the allocation is going to be made, a non-uniform memory access, right. Now, the third one is cache coherence. So, somewhere your memory needs to be looked into. If you provide a cache coherence, local memory, so that it becomes easy for it to access when it is providing, where there this concept of cache coherence comes into picture, and again a cache coherence non-uniform memory access, right. Your local memory itself is going to be made to behave as a cache. That is where this cache coherence model comes into picture. The fourth one, cache coherence non-uniform memory access. So, these 4 models we are going to discuss, right, and in multi-computer we are going to discuss one model, NORAM. In multi-computer we are going to discuss NORMA, no remote memory access, right. In multi-computers we are going to discuss one model, that model is no remote memory access. So, these are the 4 models. Out of 4, 3 is going to be discussed in detail, and he has just made a mention of this, and in multi-computers we are going to discuss NORMA model, no remote memory access model. Clear? Right. So, we are going to discuss the first model, UMA, uniform memory access. The block diagram goes like this: uniform this is going to be processor 1, 2, 3, input output, shared memory 1 till n, and then system interconnection, a bus, crossbar or n cross n, the connectivity, right. Now, this is a pictorial representation of a uniform memory access multiprocessor model, right. You have got n processors P1, P2, P3 till Pn, and then you have got a IO interface, and then you have got shared memory from SM1 to SMN. All these are interconnected. This acts as one single memory module, and every processor interacts using this interconnection mechanism. I am talking about the system interconnection mechanism. There the bus, the structure for interconnection could be usually a bus, a crossbar or a n cross n interconnection mechanism, but connection mechanism we are going to study in detail in the 3rd unit. But at this point, so all the systems are going to be interconnected using a interconnection mechanism wherein each processor is given access to the memory, right. You have a IO interface, and remember every processor has got a equal share of accessing any memory module. That is where the concept of uniform memory access comes into picture. Clear with this? This is what your uniform memory access model is all about. Clear? Right. Right. We will go to the next one, non-uniform memory access model. Non-uniform memory access model. Again, there are 2 here. One could be, there are 2 approaches. The first one is a shared memory, or it could be hierarchical structure. hierarchical structure in sharing. Again there could be a shared local memory or it could be a hierarchical structure used for sharing in a non-uniform memory access models. So, we will look into both of this now. One, interconnection mechanism, and then you have got a processor. To the processor again you have got local memory, like that you have got N, and then processor 1, processor N, right. This is connected to this. Example of a representation of a non-uniform memory access model, right. Now, you have got a local memory attached to each processor and then interconnected by a interconnecting system, interconnecting mechanism, right. Now, what is the difference that you can make out from the previous one and here and this one? The way the memory access is provided. There it is a uniform memory access to every processor, but here even though a processor can access other memory, but the way it is provided is not uniform. P1 has got more access to memory 1 when compared with the other one, right. Now, this is with respect to a local memory, but when you look into the hierarchical one, wherein you are using a global mechanism, and remember this are globally addressed. When I use the word globally addressed means every memory can be accessed by every other processor. The way the naming convention, the storing etc., is global in nature. So, any processor can access any memory location. It is not that this memory is a local cache to this processor. It is not a local cache, it is a memory wherein anyone can access other one, right. This is for local memory is addressed globally. This is a shared local memory concept. Now, a small modification to this is nothing but a hierarchical approach. The hierarchical approach is going to be like this. This is going to be processor 1, processor 2, processor N. So, it is clusters. You have got one cluster, likewise you have got N cluster. Because you have got and then right. This is a non-uniform memory access method, right. You have a globally interconnected network and you have a cluster. When you look into this each cluster, it is simply a UAM model, uniform memory access model, wherein you have a processor, interconnection system, and again a memory. Again this could be either few UAMs combined together. So, inside a NUAM it could be UAM. This cluster can act as a uniform memory access model, a processor, a memory being shared, and this is the cluster shared memory. For this cluster, this is the shared memory, and then it is going to be coming. Likewise, you could have n number of clusters. This is where the hierarchy 1, inside that again you have a one more hierarchy. This is where the hierarchy access model comes into picture, non-uniform hierarchical accessing model, because there is one hierarchy defined. Above this there is one more hierarchy that is being defined. Here this communication system is only for communicating among this processors and shared memory, but whereas this communication system is to communicate among all the clusters. So, there is one hierarchy, above that is one more hierarchy, that is where the concept of hierarchy came into picture here, right. And again globally shared memory, you have got globally shared memory, again that is connected by a interconnection network, clear. So, that is why we call it as a non-uniform memory access. It could be a local shared one wherein access are going to be different, or it could be a uniformly shared memory access wherein each user is going to be given a access wherein the different hierarchies are going to be defined. Each cluster, as I said, no, it could be again a uniform access or it could be a non-uniform access. Above this cluster you have got all these clusters are grouped together by a interconnection mechanism, right. So, that is where the concept of hierarchy comes into picture. Now, if you look into the block diagram, a few more could be understood. Clear with this? We will go to the third one. What is the third one? COMA. COMA, cache only memory access, cache only memory access. Now, if you look into the block, so it is going to be interconnection network, interconnection, you have CP, DCP, right. Cache only memory access model, we have got a directory, a local cache and then a processing. Likewise, you have got n clusters interconnected to a interconnection network. Now, this is what COMA model is all about. I said no, depending upon the interconnection, either it could be a local or it could be a global one, right. Now, with this we are going to complete our discussion with respect to multiprocessors. One more model, CCNOMU, cache coherence, non-uniform memory access. He has just made a mention, he has not gone in detail into it, clear. Now, with this I am going to end my today's discussion. In the next class we are going to look into the multi-computer models, right. Your textbook has defined one model and then we will look into the other issues in the next class. So, with this I am going to end my session. Thank you for patience listening.